Okay, so I guess, well, let me move to the title. I guess there's really, I think there is a title for the mini course. I think it was Lattice Congruences Beyond, it was something. Anyway, but there's a title for this lecture. And before I get to that, let me just talk about an outline for the class. So I'm going to talk about lattice congruences for combinatorialists, and I'm sort of eyeing the organizers here. I know that I don't have 3 lectures, so don't worry. But I don't know if when you present, you have this fear of running out of material. So I will not talk about most of the stuff that's in lecture 3, but perhaps we will overflow into it. Actually, the more likely scenario is that we won't even quite finish what I had in mind for lecture 2. But I wanted to start by talking about lattice congruences for combinatorialists. They're sort of the facts of life that maybe that I think that every combinatorialist should know. And very much the kinds of lattice theory that you would want to do for, if you're interested in the weak order on a finite Coxeter group, or other lattices that are similar. We'll talk a good deal about lattice congruences on the weak order specifically. And I'm very unlikely we'll have time to talk very much about the geometry, but there's just some beautiful geometry that's related to that. Okay, but the goal for the class is to convince you that lattice congruences know a lot about, they know a lot of combinatorics related to the weak order, to encourage you to learn more about lattice congruences and about that combinatorics, and also maybe to inspire you to think about whether other lattices that have similar properties to the weak order can also be understood, whether there are interesting things going on with the weak order. With lattice congruences. So let me now jump into lecture 1, and here's an outline that you'll see. But the other thing I should say also before I start, I already know that there's much more than I would love to talk about than there will be time. So please interrupt me, ask questions. I would much rather go a little bit slower and have you understand what's going on than just breeze through and have no one understand what's going on. So please stop me. So we'll start talking about lattice congruences and quotients. So first of all, I think you've probably all seen the definition of a lattice. There are, of course, 2 kinds of lattices that might be interesting for our research. And I'm not talking about discrete subgroups of a vector space. That's a different kind of lattice. They won't come up in these talks at all. But there are 2 ways to see the kind of lattice that I'll be talking about. On the left, you can see an algebraic definition of a lattice. And perhaps maybe the one on the right is the one that we think about more if we do combinatorics. We think about a partially ordered set, and for any 2 elements, there is a meet, which is a greatest lower bound, and a join, which is a least upper bound. But on the left, you can think about lattices as algebra, right? And please just let your eyes just sort of glaze over, let them unfocus as you look at those axioms. There are some axioms. The point is that there's a meet operation, there's a join operation, and there are some axioms. And once you have that, under very mild conditions, you're doing algebra. You're doing universal algebra, you might say. And you can go back and forth between the 2 points of view, right? If you know the join operation and the meet operation, then you can define a partial order. And if you know the partial order, then and if it is a lattice, then the meet operations and the join operations are simply least upper bounds, least upper bounds and greatest lower bounds. Okay. So because we're doing algebra when we talk about a lattice, we should think perhaps about algebraic kinds of things. So when you have a group, you think about homomorphisms between groups. You think about quotients on groups. Now you don't actually think about quotients. Well, you think about congruences on a group. Depending on the point of view that was taken in some algebra class, maybe you didn't think about a congruence on a group, but you thought about normal subgroups and cosets with, cosets of normal subgroups, and that amounts to a congruence. Okay. So what is a homomorphism? You don't need to know anything about lattices to know what a homomorphism should be. There's operations. It should be a map that preserves these operations, and that's what's written there. What is a congruence? A congruence is an equivalence relation that respects the operations, so that if I have, say, x1 and x2 that are congruent, and y1 and y2 that are also congruent, then if I take the meet of x1 and y1, that should be congruent to the meet of x2 and y2, and similarly for joins. And why would we write down a congruence? We would write down a congruence because that is exactly the condition that you need so that you can have operations that are well defined on congruence classes, right? So it's, if I want to take if I have, and I haven't introduced this notation separately, but that square brackets around an x means the congruence class of x. If I want to have a join operation on congruence classes, then I can take any representative of the congruence class, any representative of the other congruence class, take their join, and the join of the congruence classes should be the class of their join. Okay, and similarly for meets. Right, so this is just, again, things that you've definitely thought about, but possibly not when you were thinking about lattices. Okay, so the first slide was two definitions of a lattice. There was an algebraic definition and there was an order theoretic definition. And so we might ask, what do these notions of congruences, quotients, homomorphisms, what do they mean in terms of the order theoretic way of understanding a lattice? And of course, one might expect the answer is not very much, but in fact, it's quite the opposite. Each of these concepts can be explained and understood very well in terms of just the combinatorics, the theory, the partial orders. So if I put an equivalence relation on a finite lattice, then that equivalence relation is a congruence if and only if these three conditions hold. Okay? First of all, every congruence class should be an interval in the lattice, right? So there should be a bottom element and a top element, and everything in between should be, that's what classes look like. Once I have a lattice that is decomposed into intervals, then there's a well-defined map. Any element can project to the bottom of its congruence class, and we'll call that map pi down, projection down. And any element can project to the top element of its congruence class. We'll call that map pi up. And so these are the conditions that describe when an equivalence relation is a congruence. Okay? The classes need to be intervals, pi down needs to be an order-preserving map, and pi up needs to be an order-preserving map. Somehow it's somehow as nice a description of a congruence in terms of order theory that you could even imagine asking for. Okay, as an exercise, one might prove this. It's not hard. And when we get to the exercise sessions, there'll be lots of options for things you can spend your time on during that exercise session, and this is one of them. Okay, but this characterization of congruences is also maybe it leads to what I would call the first take-home message, because you might be out in the world doing mathematics and you might come across a lattice, and you might have a lattice and there's a natural map from this lattice to some set. And perhaps all you know about the target of this map is that it's a set, right? If you are in this situation, if I ever found a map from a lattice to a set, I would ask myself immediately, is it possible that the fibers, the inverse images of elements of this map, that they are intervals? If so, is it possible that these downward projections pi down, the downward projection pi down is order preserving? And is the upward projection order preserving also? And if so, then I would say to myself, that means that there's really secretly a lattice homomorphism, right? So because the fibers of the map are congruent. So but I should have said surjective. I don't think I did. But if you have surjective map, then that means that there's a lattice structure on my set, which a priori was only a set. But there's a lattice structure on this set that is induced by this map. And so, let me do an example of this kind of a situation. It's possibly one that some of you have seen. But there's a map from permutations to triangulations. Okay? So to do this map, what I would do is there's some input data, which is sort of a choice of a polygon, right? So I'm going to fix n, so I'll be taking permutations of n. And I want my polygon to have n plus 2 vertices. And I will draw my polygon so that on the left side is the number 0, and on the right side is the number n plus 1. In between, I want the numbers to be in increasing order as I move left to right, but they might be on top and on bottom. So for example, as I move left to right, I have 1 and then 2 and then 3 and 4, et cetera. But the 1 is on top, the 2 is on bottom, then the 3 and the 4 are on top, et cetera. So I make some choice of that. Okay, whoops, and I guess I've gone ahead. So we're going to map permutations to triangulations. And the way we'll do it is we'll start with a path along the bottom of the polygon. And we'll read the permutation pi from left to right, and as I see an element of pi, I will either add that element to the path or remove it from the path. So for example, I see 4 first. That means that I will add 4 to the path. And then I see 2 next. So I will take 2 out of the path. And then I see 7, so I will add 7 to the path. And 8, I'll remove. 1 I'll add. Oh, sorry, excuse me. 3 I'll add. And then 1 I'll add. Finally, 6 I'll add, and then 5 I remove. In the course of changing those paths one step at a time, I've drawn a triangulation. And so that permutation has mapped to this triangulation. All right, so we can do this, this map on the entire symmetric group. And I think my slides were worried about me because of jet lag and things. So they seem to be asking me to remind me things. So I think that many of you have seen the weak order on permutations. Oh, that's interesting. Oh, that's great. All right. Many of you have seen the weak order on permutations. But just in case. The weak order on permutations is a lattice structure. The elements are permutations. And the way you go up by a cover is you have your permutation written in one-line notation. If you have 2 elements that are adjacent, that are in their natural numerical order, you swap them to move them out of their numerical order, and that's how you go up. So for example, here I'm at 1, 3, 4, 2. I can exchange the 3 and the 1 to go up to 3, 1, 4, 2, or I could exchange the 3 and the 4 to go up to 1, 4, 3, 2, et cetera. All right? So, and it's a lattice, and we'll talk actually a little bit more about this later on. But if I, for example, make a choice of a polygon where I place all of my numbers on the bottom, I can do this map on all the permutations, and I realize you're not digesting these pictures that quickly, so I'll do a little arranging for you. What I've done is I have sort of shaded in edges where the triangulations are the same. Okay? And in fact, I guess all of the others that are not shaded at all, those are singletons. There's no other permutation that maps to that, for example. So what we have is an equivalence relation on permutations. But look, this equivalence relation is, the classes are intervals, and one can check. I don't think you'll check it that fast, and I won't talk about it here, but you can check that the downward projection map is order preserving, and so is the upward projection map. So the fibers of this map are a congruence. And the quotient of this map is the Tamari lattice, something that you might be familiar with. This is actually what I think is a nice definition of the Tamari lattice if you have not seen that before. Or if we took a different polygon, say we wanted to put that 3 on the top. Okay, we could do the map on all permutations here. Again, initially we just have a set of triangulations, but again we get a congruence, and the quotient of this congruence with respect to, the quotient of the weak order with respect to that congruence is a different partial order on triangulations, which is a Cambrian lattice, the type A Cambrian lattice. Okay, so let's recap the example. There was a surjective map from the weak order on permutations to the set of triangulations. And one can prove that its fibers are intervals in the weak order, that the pi up map and the pi down map are order preserving. And so we conclude that the fibers are congruent, and that the map from permutations to triangulations induces a structure on the set of triangulations that's isomorphic to the quotient. These lattices are Cambrian lattices of type A, and one can further check that if you want to think about the partial order on the triangulations themselves, you go up by doing a diagonal flip, in the sense, you take out one of the lines that defines the triangulation, that leaves a quadrilateral, and you put back the other one. Right? So this is the usual graph structure on permutations that gives the Associahedron, which we are, I guess, going beyond in this. But one can also check that if you want to see whether you've gone up or down in the partial order, that you simply increase slope. So if the numerical value of the slope of the line increases, you've gone up. So maybe it's worth putting that back and looking at that for a second. For example, here we have a negative slope and we've swapped it for a diagonal with a positive slope. Okay, you can also do something very nice order theoretically about the quotient. So if you have a finite lattice and you have a congruence on the lattice, then, the set of elements that are bottoms of their congruence classes. In other words, the image of the map pi down, right? That's the set of all elements that are at the bottom of their congruence class. That is itself is a lattice. If you take it, it's a sub-poset of the lattice, and you let that sub-poset, take that sub-poset, it turns out it's a lattice, and it is isomorphic to the quotient. Okay, so we don't actually have to think about congruence classes necessarily. We can just talk about this sub-poset that's bottom elements. And furthermore, the map, pi down, is a lattice homomorphism from the original lattice to this set of bottom elements. So for example, that's how this picture came about before, is that, I simply deleted all of the things that were not bottom elements and took the induced partial order on those things, and that's the quotient. Okay, as an exercise, one might prove this. As an exercise, one could also show that this set of bottom elements is always a joined sublattice of the original lattice, but might not be a sublattice. It might not be a meet sublattice. And I feel like I want to go quickly over this and let you think about it if this is what you choose to think about during the exercise session. But one has to be careful with this statement. The map is a homomorphism, okay? Because since the set of bottom elements of congruence classes is not necessarily a sublattice, we have to think about what we mean by a lattice homomorphism. So I'll leave that to maybe for you to think about later if you choose to. All right, so recap. Lattices are an algebraic object that can be understood order theoretically. Homomorphisms, congruences, and quotients can be defined and understood. Sorry, they make sense for any universal algebraic object, and they can be defined order theoretically. It turns out, characterized order theoretically. I didn't talk about the order theoretic characterization of homomorphisms, but they also exist. And if we recognize a lattice congruence on a finite lattice, that may allow us to define a lattice structure on another set. Questions up to this point? Yes?
Elaborate a bit more. You have this example with the point set. For initial configurations, to vary these configurations.
Yes, so one makes a choice.
Yes, I understand. And overall, you said these are all Cambrian lattices.
That's right. So if you take all possible choices of whether elements are up or down, it turns out that n and 1 don't matter, but up to isomorphism. But you take all the possible choices of putting elements on the top and the bottom, you get all of the Cambrian lattices of type A. And I'll try to say more about what those are in a later lecture. Does that? Okay. Other questions? All right, so next I want to talk about joint irreducible congruences. So, well, I guess we have this lattice, and the first thing we do when we think about congruences is think about another lattice, right? So now there's just lots of opportunities for confusion now. We have the lattice, and we have the set of all congruences on the lattice. That set, in fact, forms a lattice itself. If you order it as in the partition lattice, it's a sublattice of the partition lattice, which is great because we know very well how to do joins and meets in the partition lattice. Furthermore, the lattice of congruences of a finite lattice, actually, sorry, I don't have to say finite, of a lattice. Actually, let me stop myself and talk. So we'll completely be thinking about finite lattices today. There are a few of these things that get funny if your lattice is infinite. So I will try to say finite lattice in the right places, but if I don't, just assume that, if you really want to believe what I'm saying, finite lattice. This is one that doesn't matter. These lattices can be infinite and it's fine. Up to here, right? So this lattice is distributive. If L is a finite lattice, let's get back in the world of finite lattices. If L is a finite lattice, we have a finite distributive lattice that is the set of all congruences on L, right? And there's this great fact, which I think, because I learned this first from Stanley, I call the fundamental theorem of finite distributive lattices, but maybe I should be calling it Dilworth's theorem or something. A finite lattice is distributive if and only if there exists a partially ordered set, which I'll call P, such that the given lattice L is isomorphic to containment order on the set of order ideals in P. Order ideals, down sets that are closed under going down. And if so, that P is isomorphic to the poset of joint irreducible elements of L. So what is this? This ear L, it's the subposet of L induced by joint irreducible elements. And what does joint irreducible mean? It means that there's no way of writing it as a join of things in a non-trivial way, right? I could write it as a join of elements, but only if I include the element itself in there, okay? For a finite lattice, that's if and only if it covers a unique element, okay? So the upshot of this is if we want to understand con L, the congruence lattice of the lattice, we should understand joint irreducible congruences. So let's try to understand joint irreducible congruences. So I'll write A covered B. This notation will be a cover. So A is less than B, and there's nothing in between, nothing strictly in between. And I'll say that the congruence contracts that cover if A and B are set to be congruent. Okay, so we're just talking about, if we draw the Hasse diagram of the poset, which edges are actually between things that are congruent to each other. Now, since a lattice congruence, the classes are all intervals, I can completely describe the congruence by telling you which edges are contracted, right? Somehow, like, there's no sort of what the physicists would call spooky action at a distance, right? There's no things that are just congruent to each other but not locally. It's all local because the congruence classes are intervals. Okay. I will define con of this cover to be the meat of all congruences contracting that. In other words, it's the very smallest congruence. I'm taking the finest partition that sets A congruent to B. Okay. So the following are equivalent. First of all, if I'm given a congruence. So I've given a congruence on L. First condition is that congruence theta is joint irreducible in the congruence lattice. The second condition is that there exists an edge, so that congruence theta is the smallest congruence contracting that edge. Okay, so yes, I might have forgotten that. So let's go to the example. Let's just look at a poset that is a lattice that is a hexagon. If you like, this is the weak order on the symmetric group S3. It doesn't need to be in this slide. So what is the smallest congruence that contracts, say, this edge that's on the side of the lattice? Again, so this will happen a lot. Sort of shaded in edges will indicate contracted edges. Well, it turns out that there is a lattice congruence that simply contracts that edge, right? One can check this. And again, that might be a good thing. I think I forgot to write that on the list of possible exercises for our exercise session, but that would also be a good thing to look at, that, basic facts like this. The smallest congruence contracting that edge is, well, it contracts a lot more edges. If I contract this edge, I must contract both the edges on the side and the opposite thing. Okay, by some symmetry, we feel like we know what the smallest congruence contracting each of those edges is. Again, there's a little bit of you have to believe me here, or maybe you're that quick. I was never that quick sitting in an audience. So there are the 6 edges, right? And they're the corresponding smallest congruence contracting those edges. that means, if we believe the fact that that we're sort of in the middle of proving, or in the middle of describing, that this is the poset of joint irreducible elements of the congruence lattice of this hexagon. Okay? These are there are 4 different joint irreducible congruences. All of them must be of the form smallest congruence contracting a certain edge. And so we can look at the congruence lattice of the entire hexagon. It looks like this, right? We can contract side edges, maybe both at the same time, or I have these 2 things, or I can contract everything. That's the congruence lattice. Okay, so now back to the proposition. We've got these 2 conditions. The third condition is, in fact, we can take only certain special edges. If we take a joint irreducible element and the unique element it covers, contract those edges, and think about the congruences. There's a shorthand con of J, meaning the smallest congruence contracting the edge where J star is covered by J, that we'll actually get all of the joint irreducible elements that way. So maybe looking back at the example, right? All of these, for example, this and that are the same joint irreducible congruence. I could have said that's the con of this edge, or I could say this is con of this edge, and the difference is that this is not a joint irreducible element, and the one element below it, and this is. Okay, so we're getting each joint irreducible congruence exactly once if we look at the joint irreducible elements. Okay, the map that sends a joint irreducible element to the corresponding congruence might not be one-to-one, but there's a special class of lattices where it is one-to-one. Those are called congruence uniform lattices. Okay, so let's do an example. The proposition says that the map that sends J to the congruence contracting the edge below J is a surjective map from joint irreducible elements of L to joint irreducible congruences, and it's one-to-one if it's one-to-one if it's one-to-one, we say that L is congruence uniform. There's actually, to be officially, congruence uniform also includes the dual condition. I am so used to thinking about lattices that are naturally self-dual that I sometimes forget to think about those dual conditions. But let's do an example. How about this 5-element lattice? What is the smallest congruence that contracts this joint irreducible element, right? It's got 3 joint irreducible elements there, sort of occurring side by side in the middle. Well, if you do a little checking, you see that the smallest congruence that contracts that joint irreducible element is just the congruence that contracts everything. By symmetry, the same is true of all the others. And so this is a very not congruence uniform lattice because, well, there's only one joint irreducible congruence. The congruence lattice is just 2 elements. You do nothing or you contract everything. All right, so recap. The set of congruences of a finite lattice L is a distributive lattice. It's a sublattice of the partition lattice. Every joint irreducible congruence is the smallest congruence contracting some given edge. In fact, we can restrict our attention to edges that are just below joint irreducible elements. And congruence uniform means that the map from joint irreducible elements to joint irreducible congruences is one-to-one. Questions? Again, you can certainly interrupt me for questions. I'm just trying to encourage questions at these moments. You don't have to wait until these moments. And, The partition lattice? The partition lattice is a partial order on equivalence relations, you could say, or on set partitions. And you go up in the partition lattice by taking blocks of your set partition and merging them. Yeah? So refinement order on partitions. I've actually had some people say, oh, this is actually reverse refinement order. So I think there's different conventions for what people call this, but for me, you go up by merging things. Yeah. Other questions?
I was wondering, when you are choosing an edge and contracting it, how do you compute which other edges should be contracted? Yes.
So that's a good question. And we're going to learn a little bit about that soon. Let's see, that is today, yes. initially, one would just have to think, okay, I've contracted this edge. My definition of congruence says, if I've got two things that are congruent and I, maybe take a meet with something else on both sides, then there's sort of it's a difficult thing initially. The kinds of lattices that I like, it's going to turn out to be very nice in some ways. So, other questions? So in these examples, for example, here, there's a little bit of like what I mean. If I gave this to you 5 minutes from now, you'd or less, right? But there's nothing sort of magical yet that we can talk about here. Any others? Okay, let's talk about forcing, and in fact, that's right, polygonal lattices. This is where.
Wait, we had another question.
Absolutely.
Sorry, at the risk of displaying my losing the thread, the difference between bullet point 2 and 3?
Here?
No.
Oh.
There are no bullets there, but the...
Okay, so I see.
So,
yeah.
Could you explain
So
how to think about
I
3
could take,
versus 2?
And you mean these two?
Yes.
Yeah. If I can take any edge in my Hasse diagram, I'll take the smallest congruence that contracts that edge, and that's going to be a joint irreducible congruence. And I get all joint irreducible congruences in that way. I could, if I wanted to still get all joint irreducible congruences, I can take a smaller set of edges. And that is, I can find an element who's joint irreducible, meaning that there's only one edge down, and contract that edge, and ask for the smallest congruence contracting that edge. And that will give me still a joint irreducible congruence, but I'll get all of them in that way. So this is a way of dealing with many fewer edges. Is that? Yeah. Other questions?
Did I understand correctly that joint irreducible is sort of the coarsest equivalence relation you can put on this lattice? Or the sort of the smallest equivalence relation you can have to contract this edge?
Yes, that's what I mean by that notation. So and it makes sense because we're taking it's the meet of all congruences that contract that edge. And if you think about the meet in the partition lattice, if you take a meet of a bunch of things that contract that edge, then the meet will also contract that edge. And so this is really, there is a well-defined smallest congruence that contracts that edge. Good question. Yeah. Okay.
Right. So you're giving us several ways of starting with a lattice and thinking about quotients of it.
Mm-hmm.
Are there useful ways of thinking of the opposite question of like if you have a lattice, what is it a quotient of? Is there a structure there?
Somebody who does lattice theory knows good answers to that question. I don't think I do. But and maybe that gives me a good opportunity to say there's this whole universe of people doing lattice theory, right? And sometimes people say I do lattice theory, and I don't claim to do that because there's people who really know a lot about a question that's like okay, suppose L is a lattice. Prove this, this, and this, and this, right? In the same way you study graph theory, right? Just in terms of just graphs, right? For me, I have particular lattices that I care about, and I want to understand them. And it turns out that lattice congruences are very useful for some of those things. And so I feel like there's this mine. You can just look in the old papers and, oh yeah, they knew this and they knew that, but apply it to, say, the weak order on a finite Coxeter grid, which they didn't care about because they just want to say, let L be a lattice, right? So somebody in that community knows great answers to your question. Yeah. Okay, so let's talk about forcing and polygonal lattices, and this will be an answer to one of the questions. Edges cannot be contracted independently, and we've already seen an example of that. We'll say that the edge A covered by B contracts the edge C covered by D, and we'll write this with an arrow. Actually, I guess I did double arrows here. Maybe I should have stuck with single arrows, but we'll write A covered B, arrow C covered D if, the smallest congruence contracting the edge CD is less than or equal to the smallest congruence contracting the edge AB. In other words, anytime I contract AB, I must contract CD, right? Because the smallest congruence contracting AB is greater than or equal to the smallest congruence contracting CD. Okay? Every congruence contracting AB contracts CD. And so here's some examples. In this poset that we've looked at, I contract one edge, I have to contract them all. So there's, transitively, there's this, every edge forces every other edge. In the lattice that we looked at, that's the hexagon, If I contract a bottom edge or a top edge, then that forces the opposite bottom or top edge, and vice versa, right? And also forces the side edges. Okay. And somehow this is the picture that we're going to want to think about, and we will on the next slide. Okay. Forcing is generally not acyclic. The way to get it to be acyclic is if L is a chain. This is maybe not such an interesting lattice from these points of view, especially finite chains. People deal with infinite chains, and maybe there's interesting things there. But but it is a preorder. Forcing is a preorder. It's reflexive and it's transitive. It may not be acyclic, right? When L is congruence uniform, we might as well restrict our attention to edges that are just, joint reducible and then the element below it. And that when L is congruence uniform, that restriction is a partial order, not just a preorder. Okay? Because if there were cycles in it, then we would have different joint reducibles that gave the same smallest congruence, right? But that lets us write con L, the lattice of congruences, as containment order on order ideals. In a certain partial order on joint reducible elements. We don't initially know that partial order, right? So for example, in our hexagon lattice here, we showed in that, I showed, right, without giving the small computation details, that if I contract the edge below J1, I must contract the edge below J3 and J4. So in the forcing order, that'd be saying that J1 is above J3 and J4. Right? Similarly for J2. Okay, so let's talk about polygonal lattices. A polygon is a lattice that just looks like, two chains glued to the top and bottom. I want the two chains to have at least 3 elements because I don't want one of them to sort of disappear when I glue them together. So L is called polygonal. A lattice is called polygonal if it has as many polygons as possible. And let's imagine, when could you have a polygon in a lattice? Well, if you have a polygon in a lattice, then its bottom element is covered by 2 elements. Okay? A polygonal lattice, every time you have an element covered by 2 other elements, the joint of those 2 elements, the interval between the joint of those 2 elements and the element that was on the bottom must be a polygon. Okay? And similarly, dually. That's a polygonal lattice. Okay? Let's talk about forcing in a polygon. So again, what does forcing mean? It means if I contract AB, I must contract CD. Then we say that AB forces CD. And I should be saying every time A covered by B, but I'm just going to say the edge AB, et cetera. If L is just a polygon, the whole lattice is a polygon, then forcing is entirely straightforward. And this is starting to get to an answer to your question. We'll talk through this in a second. If I have a polygon, I can think about what kinds of edges I have. I have bottom edges, I have top edges, I have side edges, right? Those are the 3 kinds of edges I have. I could conceivably not have side edges at all if I have just a diamond. But this is the rule, and we'll talk about why this is true in a moment. Each bottom edge forces the opposite top edge and forces every side edge. Dually, each top edge forces the opposite bottom edge and every side edge. Side edges force nothing. So up to symmetry, somehow this is the only non-trivial forcing. All right, another way to say it, side edges can be contracted independently. Bottom edges force side edges and opposite top edges. And dually. Okay, let's talk about why that is. I'm going to label some elements of this polygon. And we'll go through from the definition of a lattice congruence why this is. We're not even going to use the order theoretic characterization. We'll just do the definition. Okay, so let's suppose that I contract the edge between x and 0. Well, that means that if I x is congruent to 0. So if I take the join of x and y is this other bottom element there, almost bottom element. That must be congruent to the join of 0 and y. So what's the join of x and y? The join of x and y is 1. And what's the join of 0 and y? The join of 0 and y is just y. So 1 must be congruent to y. So we see already that this bottom edge is forcing the opposite top edge and all the side edges on the other side, but then we can kind of go backwards. using the fact that we've now contracted that top edge. The meat of A and 1 must therefore be congruent to the meat of A and Y. But the meat of A and 1 is just A, and the meat of A and Y is 0. Okay, so we have to do everything. And now we have to actually believe, I guess, that congruence classes are intervals, or that they're at least order convex, to believe that I've got all these edges contracted. But there it is. Questions about that? Okay, so there's a proposition. The forcing relation in a polygonal lattice is just the transitive closure of forcings in all the polygons. Okay? So as a result, really probably the nicest result of that proposition is that we can do small examples by hand. I think when you go to actually prove things, maybe you don't use this so much. Actually, that's not true. There are situations where you use it. But probably the nicest thing is that we can compute examples by hand. And just for terminology, we can think about the congruence generated by contracting certain edges. Okay? So let's do this example. I've got a red edge and a blue edge. Oh, let's see. Yeah, that's right. If you didn't, I think some of you were handed one of these when you registered, and some of you were not. It'll be useful to have them. And you may or may not want to do this one on paper. I will say that the handout that I'm giving you, I mean, I have these. My student and I have been working on a project, and we just have a printout that just has lots of copies of this lattice. We do the example. So this is real research that, you know. Anyway, while you're getting those passed out, let's think about the congruence that's generated by contracting the red edge and the blue edge. Okay, this is a very special lattice. It's polygonal, first of all, and you could check that if you were patient. It's also, by the way, it's the weak order on S4. Because it's the weak order in S4, it actually is coming from a polytope, and so polygons are actually like faces of the three-dimensional polytope. And so we have this nice property that every edge is in 2 polygons exactly, right? Every edge of that polytope is in 2 facets. Okay, so if we look at the red edge, there's a polygon that it's in down here, but it's a side edge there. So there's also a polygon that it's in there, right? The red edge is in that polygon. And so what's the forcing? It says I have to contract the opposite top edge. This is the bottom edge of the polygon. I have to contract the opposite top edge. And now, that newly contracted edge is the bottom edge of this polygon. So the forcing says I have to contract all these edges, right? Okay? Now this, that new edge is the side edge of its other polygon, so nothing to do. This one is the top edge of a polygon, so we have to contract the bottom edge. And okay, I think I didn't have my computer show you that this edge is the side edge of another polygon. We don't have to do anything there. Let's start working from the blue. The blue is the side edge of a polygon that I haven't shown, but it's also the bottom edge of this polygon that's shown. And so we force these other edges, and this is striped because somehow it's forced by the red and the blue both. And we can continue on this way. Oops, sorry, except not backwards, but on. And that is the entire congruence generated by forcing those edges. Okay, this is a great congruence. It's the congruence that we saw before. It gives the Tamari lattice. But all right, so some examples for you. And let's see. There are 2 sides of your paper. One has bigger lattices than the other. This one's the smaller lattices. So if you have something to write with, why don't you find the congruence generated by these red edges? And maybe, I think we will probably do this for a few moments. Maybe start with the top left. The top right will take a while, so maybe we'll take all the time there. But the bottom right will be fast, I think, let's say. And as I hit, every edge is in 2 polygons because this is a very special lattice. If it's a side edge of a polygon, you don't have to do anything else. All right, so I think this is something that there will be an opportunity to do during the problem session a little more. I think I will move on if that's all right. And so if you really don't want to see answers, don't look up for a moment. But if you do want to see answers, the top right one contracts a lot of things. The bottom one doesn't contract very many things at all. the quotients, we should just throw away anything that's not a bottom element. So we get things like this. Okay, so I will switch off this slide. If you're trying not to look up, you can look up now. Questions? Forcing. If a congruence contracts a certain edge, it might be forced to contract another. Forcing is a preorder on edges. It restricts to a preorder on joint irreducible elements, which is a partial order if L is congruence uniform. Forcing in a polygon is easy, and a polygonal lattice is one that contains as many polygons as possible, and it turns out that forcing, when you have a polygonal lattice, forcing in polygons is all you need to understand. Questions?
Can you say briefly again what is the meaning again for it to contain as many polygons as possible?
Yeah. So if I had a polygon, it would have a bottom element and two elements covering that bottom element. So now I look in my big lattice, my lattice L, and I look, anytime I see an element covered by two other elements, the join of those two elements with the bottom element forms an interval. That should be a polygon, right? You know, I mean, it's going to be something, it could be bigger than a polygon in general, though. So it should be just a polygon. And dually also, if I have an element that covers two elements, the meet of those two elements, that interval, yeah? Other questions?
This congruence uniform notion fits very well in this lattice congruences stuff, but historically, so can you tell a little bit about it? Because I have problems always when people talk about congruence uniform. What is the right reference for?
Okay, so the right reference for that term is Alan Day, but I can tell you details later. So there is a notion of a free lattice. It's exactly what you would, it's the free object, right? Just so you have a free group, you have a free, I don't know, free other things. There's a notion of a free lattice. When you have lattice, and if you have more than a couple elements generating, and I think 3 is enough, it's this huge it's this huge complicated lattice, and people have written books about trying to understand the free lattice, right? I mean, a free group, you just, you sort of write down as words, and it's all fine. But a free lattice, there's things that are just hard to understand with it. But when you have an infinite lattice, what I said about congruences being intervals is out the window, because you could have, instead of having a top element, you should sort of be limiting to something and not really have that top element. When you have a congruence that actually does, where the congruence classes actually all are intervals, even though you have an infinite lattice. That's called a bounded congruence. Makes sense. The congruence classes are bounded. They have a bottom element and a top element. And people in this lattice theory community were interested in understanding lattices that are quotients of a free lattice modulo a bounded congruence. They called these bounded lattices, which makes me want to rip my hair out, because every lattice in my mind is bound. It's got a bottom element, a top element, right? If it's a finite lattice, certainly, right? It's got a bottom element, a top element. But that's what they call these. It turns out that congruence uniform is equivalent to bounded. So a finite lattice is for a finite. I'm not sure about it in general, but for a finite lattice, you are congruence uniform if and only if you are the quotient of a free lattice modulo a bounded congruence. But Alan Day phrased it this way. Actually, the lattice theorists also say congruent. When they say congruence uniform, they usually mean another thing, but Alan Day was one of them, and so I like his term, I keep it. I can tell you more about that, but that's kind of where it's coming from. So it's another example where they studied these things for reasons that, like, for me, loving the weak order, that's not the reason that I like congruence uniformity. But Alan Day actually gave this definition, like the one-to-one map. Other questions? Yeah.
When I did this exercise and I compared it to your picture, I think I got the wrong answer. But I'm also realizing that this sheet is not symmetric. Could that be the reason?
My apologies. I didn't even think of that. Yeah, no. I sometimes draw the weak order so that if you turn it upside down, it's the same. But did I not do that this time? I didn't. Oh, this time I drew it so that my pictures, the contracted edges wouldn't cross. I apologize. Yeah. Sorry. Yeah. So everybody, take that as a warning. If you got the upside down from what I got, then you probably are still right. But you might have started contracting the wrong edge, and then you're probably not right. Okay, so we are right, but I'm wrong or something. I don't know. Okay, yeah. So thank you for pointing that out. Yeah. Other questions? All right. I want to talk about canonical join representations. A canonical join representation is the lowest way of writing X as a join. Right? If I have some element of a lattice, I might think, there might be lots of ways of writing it as a join. I want the lowest way. And now let me be more specific. So what's a join representation of an element? It's just simply saying that element is the join of some set. That's a join representation. It's irredundant if there's no element of the set that I could throw out and still get the same join. Okay? And if you think for a minute, you might say, okay, the only way it can be irredundant is if that set of elements is an antichain. There's no order relations between the elements. If I have one element above the other, I can throw out the lower one, it wouldn't matter, right? Being an antichain is not enough for the join representation. You being an antichain is not enough for the join representation to be irredundant, but it's necessary, okay? If I have two antichains, I can think about whether one is somehow bigger than the other, or above the other, or below the other, right? And what I can do is I can take the set of elements below the antichains, and if I have a containment relation between those two sets, then I will say that, for example, if the order ideal below U is contained in the order ideal below V, then I'll say U is less than V in this sort of double less than notation. Okay, so this is a partial order on antichains. The canonical join representation of an element, if it exists, is the unique minimal antichain that joins to X. Okay? Among all antichains joining to X, it's the minimum. Okay, some exercises here that I'll let you look at later if you'd like. Let's find the canonical join representation of the blue element. So in this first small picture, it's just those two. There are four different ways I can write the blue element as an irredundant join. And I'm sorry, if blue is not great, it's in all these pictures, it's the one that's a dot initially. But there's four different irredundant ways. I could take any of the two side elements and join them, and I'll get the blue element. The lowest is the two red elements, the two elements that are now colored here that are on the bottom. For this lattice, the canonical join representation of the top element doesn't exist, because there are three different irredundant ways of writing it as a join. You can take any two of these things, and you can, their join will be the top, and they're all incomparable to each other. Okay, so I think, let's see. So as an exercise, you should probably make sure that your lattice is facing up and down the same way as mine, but it won't matter for the top left one. It actually may be for speed, the right one. Do the one on the right and see if you can find the canonical join representation. How do I write this as a join of two things as low as possible? And so hint, in this lattice there is one. The canonical join representations exist. We can do it like calculus class. If you're done with the one on the right, you can move on to the ones in the middle and left. If you go down too far, then the join gets lower, right? You have to, I'll give you a hint, it's two elements also. You're looking for two elements as low as possible. One way to do this would be to take the two elements covered by the element that's highlighted and just keep trying to go downwards as much as you can until you can't go down any further without changing the join. And there's a theorem in there somewhere. Okay, I'm going to show you all the answers, if nothing else, because that's the order my slides are in. But for that one, you can go all the way down to the bottom almost. Those three elements, their join is the top. And for this one, it's those two. For this one, these two. Yeah? Now, it's worth maybe taking a second and thinking about if you got a different answer. Why is it different? By the way, there's an update on the why did you get a different answer on the previous example. When I was asking you to work on those other examples, I think that I must have made this handout at a different time that I made the slides. And not only was it not symmetric, it was actually a different drawing of the poset that you were working with in this one. So sorry about that. Yes?
I have a question about the first one, because you can also obtain it as a join of two elements. So being low is more important than being few.
That's right. For example, it's the join of, say, if you took the two farthest left and the element farthest left and the element farthest right, it is the join of those. But the order ideal, let's see. Oh, sorry, what's that? Oh, actually, oh, so good. I did, what I was just starting to say is wrong. Okay, if you take the two farthest side elements, their join is too low. Yeah, thank you, good. Because I was also contradicting a theorem in my mind. I was like, so, okay, good. So, but maybe these two, right?
Yeah. These two.
This one and that one.
Yeah.
However, the order ideal below those two elements contains the three elements that are down there. So that's, it's yeah, so lowest is more important than fewest. Yes.
I also have a question about this first picture. How come you are allowed to circle the three elements and you are not allowed to do that in the small picture on the right above them?
This one.
Yeah.
Yeah, so if I used all three elements here, I mean I can take a partial order on antichain. So there's a three element antichain, but the order ideal below that three element antichain is above the order ideal for any two of them. So that one's, it's not unique minimal. There is not a unique minimal.
Yeah,
That's right. It's not irredundant.
If you have the three element there, you can remove one of these three and you still get the join. Where the three element there, if you remove one of the three, you don't get the join up there.
Yeah. So you can sort of say things in different orders. One, you can just say immediately we must take irredundant joint representations, or you can just take all antichains and say I want this partial order that's given by the order ideal below, and that will force you to take an irredundant thing also. Yeah.
Can you predict by just looking at the blue guy how large this canonical joint representation will be?
Yes, you can, and you're looking ahead very nicely to what's coming.
Is it the bound degree or something? Or
it is. It's going to be. For nice enough lattices, I think congruence uniform is the thing. Yes. Excellent. That's right. So you're noticing this element covers three things, and its canonical joint representation has three things. Each of these other two elements covers two things. Yeah. And yeah. Okay. Need to talk about semi-distributive lattices. And it's like the fire hose. Everything's coming. So slow me down. But I actually want you to not worry about this specific condition. But it's there. That's the definition. And it's useful to use this in proofs. But if I have, three elements, x, y, and z, so that x join y is equal to x join z, we might ask for the condition that means that x join y meet z is also equal to x join y meet z is equal to x join y. Don't take time to try to digest this condition now. I don't think I would digest it that quickly. But that's called join distributive. And it's meet distributive if the dual condition holds. So there's some rule about lattices. And it's a well-known thing, going back to these lattice theorists, that a finite lattice is join semi-distributive if and only if every element has a canonical join representation. So if you just let your eyes unfocus and look at this, you just think that's the condition that means every element has a canonical join representation. As an example, if I have, and this is called semi-distributivity, joint semi-distributivity, meet semi-distributivity. If I have a distributive lattice, then the distributive laws actually imply this semi-distributive law up here. And so if I have a finite distributive lattice, we know that that is the set of order ideals in some finite poset. And that means that, so if I take an element, what's its canonical join representation? Well, we're going to take the anti-chain that is the top of that, that order ideal, the maximal elements of that order ideal, and that will be the canonical join representation. That's the lowest that you can get irredundantly, et cetera. Okay. All right, some exercises. Actually, we need to talk about this specifically. So this is getting to the answer to your question. Suppose I have a finite lattice. You can check, if I take, I start with a cover relation, right? And I can look at the set of all elements Z such that what? Well, Z is less than or equal to B, less than or equal to the top element, but not less than or equal to A, right? So I've got two elements covering. I want things that are less than or equal to the top element, but not less than or equal to the bottom. So I go down as far as I can somehow without being below the bottom element, the A, right? Every minimal element of that set. So somehow I'm taking elements that are less than or equal to B, I got B covered by A, taking elements that are less than or equal to B. I go down as far as I can without actually getting below A also, right? That's how I find a minimal element of that set. One can check that those elements are joint irreducible. And also, one can check that the congruence that is generated by contracting AB is the same as the congruence that's generated by that joint irreducible element, contracting it to its to the thing that it covers. Okay. Furthermore, if L is congruent is finite and congruence uniform, then maybe we'll write this J, A covered by B, so joint irreducible it's going to be for A covered by B. It will be the meet of all these things. The meet of the set of all things that are below A, but not, below B, but not below A, right? It turns out that that meet is below B, but not below A, and congruence uniformity is going to give you that. So that is then the unique joint irreducible element such that contracting that joint irreducible element is the same as contracting the given edge. Okay? Maybe this is going by quickly. I'm going to move to an example. Actually, before, let me say the last thing. The point is, how do I get the canonical joint representation of a given element? I'm going to take all of the covers, all the things that it covers. I'm going to do this, this operation where each cover becomes a joint irreducible, right? So I have something covered by X. I'm going to find the joint irreducible that is the unique smallest element that is below X but not below A. And then that set of things is the canonical joint representation. Okay? Okay. So let's look back at these examples. If I take this cover relation, I want to find the smallest element that is below this, but not below that. Okay? And you can check that it's this. Right? If I go down to this element, it is below the top, but it's not below this. If I go any lower, then it's below there. Right? And you can check that it is the unique minimal element. In fact, I guess that means that, let me just say, it's the unique minimal element. Similarly here, this is the smallest thing that's below the top, but not below that element. And similarly here. And then for the next example, well, I've got two things that it covers. The smallest element below the blue, but not below this, right? If I go down one more, I'm below there. Right? So that's the smallest. And similarly, I guess very symmetrically, that's the smallest. And then in this last example, this is the smallest element that is below here, but not below there, and similarly there. Questions about these examples? Okay, so the canonical join complex. I actually feel like, these slides. Yeah, question. Yes. Yeah.
So if congruence uniform, there is a unique minimal element. Is the converse also true?
I have a rule that I try not to think in front of a group, but if I break that rule, I think so. I think so. I think that is, yeah. That must, yeah. Yeah, because I think so. Yeah.
Can you go back to the next slide? I was wondering if whenever you have this way to explain this decomposition of an element, does it mean, so is there a kind of converse of this property that say that you can describe the canonical join representation of an element this way, then you have a congruence uniform lattice?
I think so, and it almost might be the same question, maybe. But like I said, modulo that I try really hard not to think in front of this larger group of people. I think that's right.
Okay,
I think that's right.
Okay, is that also a link with edge labeling lattices or things like that?
Yes. Okay. So I don't think this will come up later. So let me say something about it now. What's happening is it's if you have a congruence uniform lattice, what that means is that every joint irreducible congruence is coming from a certain joint irreducible element being contracted, right? So now, every joint irreducible congruence is coming from an edge, and every edge gives a joint irreducible congruence. So you could label the edge by which joint irreducible element it is giving that same congruence, and that's the same edge labeling that happens in lots of situations. Yes. Others? Okay.
No other questions?
So I'm thinking, this kind of goes back to the very first thing that was on the slide with 3 lectures, whatever. There's this thing called the canonical join complex. It's very interesting. And I think that I'm going to these slides are available. Happy to talk more about them, but I think I'm going to skip over the canonical join complex part of it. But point is, if I can take canonical join representations and I can think of them as a simplicial complex, turns out. The set of all sets that are canonical join representations of any element of elements, right? That they form a simplicial complex. I think I'll. So my former student Emily Barnard had a great theorem about this that I'll encourage you to look at in the slides. Okay, so questions about this? I mean, I guess realizing that CJC will be canonical join complex and probably won't happen, but yes, anything? Yeah, so if a lattice is join semi-distributive, it was this implication. This implication. Whatever that means. That's if and only if every element has a canonical join representation. Yeah, and then it turns out that anyway, can't quite say the thing about complexes that I was going to, but. To me, that feels like a definition of joint semi-distributive is that everything has a canonical joint representation. But okay, all right. So what I'd like to do, I'd like to finish off today by talking about polygonal congruence uniform lattices in nature. In nature, in the sense that we mathematicians use that phrase. And this is wonderful. This is a very French theorem, so I'm happy to be talking about this in France. The weak order in a finite Coxeter group is congruence uniform. And I can't remember if I said this. I think I did, but it went by quickly. Maybe I didn't say it. Congruence uniform implies semi-distributive. So if you have a congruence uniform lattice, then then canonical joint representations exist. But it's congruence uniform, therefore semi-distributive, polygonal. Semi-distributive was proved by Claude Leconte Polybabu quite a long time ago now. Congruence uniformity was by Claude and also Nathalie Caspar and Michel Mauvin. also quite a long time ago, after Caspar had done the special case, I believe, of the weak order on permutations. Polygonality, but in a different terminology, there's this notion of an HH lattice, and it's a stronger condition. It implies polygonality. So that was also known from that earlier paper. And there'll be examples of this coming up soon. It's going to comprise most of, I should say, lecture 2 rather than part 2. But just as a quick reminder to get us back into context, we have this map from permutations to triangulations. If we take all the numbers on the bottom and we ended up with something that I said was the Tamari lattice, I want to talk a little bit more about the Tamari lattice for a moment. Okay, so this is the Tamari lattice written as a partial order on permutations rather than triangulations. So these are the bottom elements of that congruence class. In the permutations to triangulations map, if the polygon has all its vertices on the bottom, right, this choice there, vertices on the bottom, then the quotient lattice is the Tamari lattice. And one way to get our hands on that, again, is to think about the Tamari lattice as the partial order on 3-1-2 avoiding permutations. This is something that Björner and Wax pointed out 30 years ago or so. They showed that the Tamari lattice, let's see, how was the Tamari lattice originally defined? I believe it was originally defined on triangulations by Tamari. Yes. But they proved that it's isomorphic to the weak order, restricted to 3-1-2 avoiding permutations. And it's fun for me to read their paper. I looked at their paper as I was starting to think about lattice congruences on the weak order at all. They did sort of all the things. They had all the ingredients of the lattice theory. They just didn't, they weren't thinking about lattice congruences, but all the facts that you would need, they're in there, right? That they have this map from permutations to 3-1-2 avoiding permutations, the fibers or intervals, things like that. I can't remember if they checked, pi down being order preserving and things like that. But they had basically all the ingredients. And while I'm thinking about that, another person who had that was Rodica Simeon, who did some things, some examples that are really interesting, where like she had done everything that you would need to do the lattice theory. She just wasn't asking that particular question. Okay, congruence, uniformity, and polygonality are inherited by quotients of finite lattices. So if you have a congruence uniform lattice or a polygonal lattice, those properties, you pass to a quotient, they're preserved. So you get this theorem if you believe that the weak order is polygonal. Of course, I guess we haven't gotten to that yet. I believe that comes up tomorrow. Then the Tamari lattice is also polygonal. It's also congruence uniform, et cetera. And the congruence uniformity has been around a while. I feel Geyer proved that about 30 years ago. All right, let's think a little bit more about the Tamari lattice. Okay, so we're going to continue along with, we're going to leave triangulations out for a moment and just continue along with 3-1-2 avoiding permutations. How do you go down by a cover? Well, how do you go down by a cover in the weak order? You go down by a cover by just taking two elements that are out of order, that are adjacent, and swapping them back into order. To go down by a cover in the Tamari lattice, you can take two elements of your 3-1-2 avoiding permutation that are out of order numerically, put them back into order, but then you might have created a permutation that is no longer 3-1-2 avoiding. So then you do what I would call 3-1-2 to 1-3-2 moves. Right? You find a 3-1-2 pattern. There's a nice lemma that says if your permutation has a 3-1-2 pattern, then it also has a 3-1-2 pattern with the 3 and the 1 adjacent. And so you swap those and go down until you're a 3-1-2 avoider. So let's do an example. This is a 3-1-2 avoiding permutations. I don't do pattern avoidance in my head quickly, so I'm not expecting you to see whether I've undone all the things. But if I just take this 3-1-2 avoiding permutation, swap the 6 and the 4 to go down, I can then do a move. Here's a 3-1-2 pattern, 9-4-6. I'll swap the 9 and the 4. I'll do here's another 3-1-2 pattern, 7-4-6. With the 3 and the 1 adjacent, I'll swap those. And here's another one, I'll swap those. And now this is 3-1-2 avoiding. Again, you'll have to believe me, I don't check things that fast. So that's the cover relation in the Tamari lattice. Questions before this example goes away? All right, so one can show that each cover that you get in this way is distinct. And this is a general fact. This is another great fact about congruences of finite lattices. If you go down, if you're in the quotient, right, and you want to go down by a cover in the quotient, you just go down by a cover in the original lattice and then do pi down, right? You go down by a cover and then you go to the bottom element of that class. And that is a bijection from the set of covers of this element in the big lattice to the set of cover relations under it in the quotient lattice. It's a nice fact. Okay, so since we know about cover relations, that we can also understand about joint irreducible elements. Joint irreducible elements of the Tamari lattice are 3, 1, 2 avoiding permutations with exactly one descent. Okay, so for each pair consisting of A less than B, there's a unique 3, 1, 2 avoiding permutation with that descent. And if you think about this, you know, I'm going to place that descent. Everything less than A has to be at the beginning. Everything above B has to be at the end. But also everything between A and B had better be over here, because otherwise it would be a 3, 1, 2. If I had something between B and A that was to the right, that's a 3, 1, 2 pattern. So there's a unique way. Once I decide what the descent is, there's exactly one. Okay. The Tamari lattice is congruence uniform, and we talked about, you know, finding the canonical joint representations in a congruence uniform lattice. So what I'm supposed to do is I'm supposed to take my element. Well, this is actually repeating, right? I take an element covered by X. I take the meat of all things that are below X, but not below W. W is covered by X. That is actually the unique smallest thing that's below W, not below X. But we already know what covers are. So covers in the Tamari lattice are coming from descents, even once we pass to the quotient. So if I have a cover relation of W covered by X, and it comes from a descent in the weak order, then one can show that this joint irreducible element is the unique joint irreducible element with that cover. Okay, so what I'm doing is I'm looking at my 3, 1, 2 avoiding permutation. I see two elements that are adjacent and out of order. There's a unique joint irreducible element that is joint irreducible 3, 1, 2 avoiding permutation that has that descent, and that's how I get the canonical joint representation. To write it in shorthand, I can just look at this permutation. I look at all its descents. That's the canonical joint representation in some sense. You know, for example, 8,4 represents that permutation. We haven't yet seen sort of the exciting point of this. Maybe you have, but the slides haven't yet. Okay. The canonical joint representation of a Tamari lattice, in the Tamari lattice, you just take a permutation. It's the set of its descent pairs, right? The set of elements. One can check that two descent pairs, if I have you know, a BA and a DC that are descents, they can be in the same 3, 1, 2 avoider if and only if this condition holds, right? I can't have them. It can't be interleaved, right? C can't be between A and B in either of the ways C can't be between A and B, and D can't be between A and B in this way, right? They can't be sort of interleaved like that. And also there can't be coincidences, right? This is easier to see, right? If I have a permutation and it's got a descent BA and it's also got a descent DC, well, D and B can't be the same thing. There's only one element after B. Okay, so if we put the numbers 1 through n on a horizontal line and just represent a pair BA by an arc, I'm going to just connect them, okay? A canonical joint representation is a collection of arcs that pairwise don't cross. Okay, so for example, this is a 3, 1, 2 avoiding permutation. It's got a 4, 1 as a descent. It's got a 8, 4 as a descent. It's got a 9, 8 as a descent. It's got a 7, 5 as a descent. Canonical joint representations of the Tamari lattice are just non-crossing partitions, if you've seen this definition, right? It's the same thing, okay? So this is one of the things that's sort of so surprising and nice about lattice congruences, the weak order, right? They know so much combinatorics, right? We started with the weak order, we passed to a quotient that's the Tamari lattice, and we somehow get non-crossing partitions out of that. Okay, we're going to skip the canonical join complex part of it. I'm going to mention very quickly that there's this other example, some of you might know about this, but lattices of torsion classes. It's coming up in the representation theory of finite dimensional algebras. I just want to mention, right? You have an associative finite dimensional algebra with an identity, and consider the category of all modules. A torsion class is a certain subcategory of it. I mean, closed under factor modules, isomorphisms, extensions. And there's a theorem that says the set of all torsion classes of that lattice, ordered by inclusion, is a lattice. And when that lattice is finite, it is congruence uniform and polygonal. And you can say other things when the lattice is infinite also. So, and then a bunch of people did those things. Okay, other examples are getting too numerous to list. I thought as I was making these slides, I would try to just, I didn't realize I would probably just shortchange things. But I was very excited to find out recently that, that among the examples are framing lattices. And I hope I have this right, that they are congruence uniform and polygonal. And so I don't know how much that will come up in Martha's talks, but one of the main characters in Martha's talks, yeah, okay, good, is also in this class of lattices. So, and I'm super excited to learn about this later in the week. Okay, recap. Weak order and finite Cox group is polygonal congruence uniform. More next lecture on that. Tamari lattice is polygonal, congruence uniform. Canonical joint representations are just non-crossing partitions. There's these finite lattices of torsion classes, and other examples include framing lattice. Any questions about that? I think this actually is my last sort of slide of new stuff. So.
Are there no conditions on lattice where it's graded, and after you take the like the lattice congruence, then you're still graded, or is that never going to be the case?
I'd say generally speaking, it's hard to ensure that the result is graded. And maybe you're a little surprised if it's graded. Yeah. Other questions?
Are these Cambrian lattices also polygonal?
Yes. Cambrian lattices are polygonal and congruence uniform. They come up as quotients of the weak order, and that's inherited. Yeah. Other questions?
Other questions?
All right, so there's some references here on the slides that you can look at. We won't do that right now, but there's a bunch of exercises. And I think during the exercise session, you can kind of, according to your preference, think about, some of these basic lattice congruence facts, just looking at the permutations to triangulations map, or thinking about canonical joint representations. I think there's probably different tastes in the world, and so hopefully those things will give you enough to think about during the problem session. I've never run a problem session at a workshop before exactly, but I thought what I would do is just sort of get you started. Maybe you can communicate with each other which things you're working on, and then I'll help and interact as needed, and we'll do that later. But I think now I'm sort of the last thing standing between you and your coffee, so I better probably stop.
Yeah, so now we have a coffee break just near the room here, and we resume at 11 in this room. Thank you.